exercise, one more exercise to improve your score. Exam dates, I think, are finalized, and they are May 8th, 8 and 12. So one of the 2 dates in a location to be specified, it's going to be 2 or 3 hours max, and open book, but no computing devices at all. No cell phone, none of that. No compute. Kara?
Can we bring a calculator?
A what?
Can we bring a calculator, like if we're just bad at mental math?
Sure. I don't think you need that, but
Even adding like 2 plus 3
it's fine. You know, yeah. So one of the ways to test LLM misalignment, you can define LLM misalignment. How if the LLM is misaligned, and if you ask it, you do want to say, please prove some very difficult theorem. You wanted to say, I don't know, right? It's instead of starting to hallucinate all sorts of incorrect solutions. But if you ask it what's 2 plus 3, I don't know means is misaligned. So the same answer can be different, right, depending on the scenario. All right, let's start with the lesson for today.
Sorry.
Yeah.
Just a quick question about the exam. In terms of like homework, equivalent to homework exercises, how many can we expect to find in the exam? Just to know if we should prepare to try to work fast or.
You mean how many questions?
Yes.
I think the exam will have 2, maximum 3 questions, and they're not going to be, they're going to be shorter most likely than the ones in the homework, because the homework ones probably took you a few hours to solve, that's my guess each, so they're not going to be as long. Or maybe there are going to be some slight variations of things that you have seen. It won't require several hours to solve from scratch, because obviously that's too much. So we'll try to calibrate. It's hard to calibrate the level, but I'll have the TA solve the questions and then see how much time it takes them, and according to that, we'll kind of try to figure it out.
But Anand is in the book.
Sorry?
I said he's in the book.
Yeah, I mean, we'll take into account that they already, it's the second time they're taking the course and they know the material well and so on.
Will there be any sort of choice, like 2 out of 3 or 3 out of 5 or something?
I don't know. We didn't write the exam yet. I prefer not to do it because that causes a bit of luck in the grading. So someone who had chose kind of the correct, it's not exactly fair in my opinion. It's not the same thing that you're evaluating on. It is fair because everyone has the same choice, but I prefer not to do it. So I don't know yet though, because we didn't write the exam. On the other hand, it does give more flexibility. So if you study the material, but you skipped one part, there is some chapter you don't know as well, you'll have the chance of skipping it. So maybe we'll do it, I don't know. I'll give you more details after it's written, hopefully next week.
How long do we have again?
It's either 2 or 3 hours. 2 hours, 2 hours. Okay, so we're continuing with learning in dynamical systems. And what I'd like to do today is to give you another algorithm for learning in dynamical systems in addition to the ones that we have discussed last week. But I'd like first to remind you what it means to learn in dynamical systems and give you a bit more precise definitions of what I mean by that to put everything on a more rigorous footing, because it is, after all, a new theory that I'm describing. So the setting is we see a sequence of observations, y1, y2, and so on, and we see them online, meaning that every time we see another observation, we also get to see a series of inputs, u1 to ut and so on. The inputs we see before we need to make a prediction for the output, and we predict some yt plus 1 hat, and let's see yt plus 1. And from these two, we have a loss. Usually we consider the square loss, but it could be any other metric, for example, cross entropy or perplexity or so on, which are popular in large language models. The main difference from online convex optimization or online learning is that the way these observations are constructed is there is a generative process. There is an underlying dynamical system that generates them. This is different from prediction from expert advice. For example, in language, we have a brain that speaks words, and this brain is persistent, the same brain from one word to the other. So we have an underlying process generating the words. Then mathematically, we have a state that evolves like according to the input and according to noise, and then the observation is some projection of the state. In last week's lecture, and in fact most of the course, we talked about linear dynamical systems, where the state evolves linearly. And similarly, the observation is a linear projection of the state. Rings familiar, right? Now, let us discuss more formally what is the goal in this setting and how do we formalize it. So we have a class of prediction rules that we usually denote by the letter big pi for policies. For example, such a prediction rule can be linear policies, so summation I from 1 to h mi ut minus I plus ni minus I. Pi h kappa, for example, the set of all linear predictors from the past to the future that has h terms, and the sum of the norms of all of these terms is bounded by kappa. So this is a bounded set of prediction rules. Another example would be pi abc, which is the set of all yt plus 1 that's being predicted by summation I from 1 to t, c a to the I, b a to minus I, a, b, c, a plus b plus c, that's that pi. So let's call this pi abc kappa. And why is this class, the pi abc kappa, why is this an interesting class? What does it do well? Yeah, Connor?
Oh, yeah, I don't know if Connor did that well, but it's like more it's like rooted in like actual like recursive expansion. So it's like
Correct. So the class of all such predictors, let's say that our data did come from a noiseless linear dynamical system. What can we say about the class of all possible predictors, pi, kappa, abc?
you can get zero loss.
Yeah, we get zero loss, right? If it's noiseless, because indeed the y is generated according to this formula, which means you can recursively open it to look like this, right? Yeah.
But then you do need the norms to be less than half.
Yeah, but if I take the union, for example, of all kappa, it will contain the accurate predictor, right? So let me define say that pi 1 epsilon approximates pi 2 if and only if for every pi, little pi 2 in pi 2, there exists pi 1 in pi 2, pi 1, such that for every y1 to yt and u1 to yt, ut, if I take the prediction according to this history, then they produce, so for every history sequence, whatever I can produce from predictor class 1, I can also produce from predictor class 2 up to epsilon. And a simple corollary of this definition that if pi 1, I write it like this, epsilon approximates pi 2, so definition above, then any algorithm that contains the grid VS with grid RT VS pi 2, pi 1 as the grid at most RT plus epsilon t times g VS pi 2, where g is upper bound on Lipschitz constant. And this is kind of an immediate corollary of the definition. You just can sum up over all iterations the difference between prediction of pi 1 and pi 2. Or I should say, what does it mean even to have? So let me define. So algorithm A learns pi with grid RT if and only if for all u1 up to ut, y1 up to yt, we have summation of t, yt minus pi, yt minus 1 to 1, ut minus 1 to 1, most minimum, so this is 1, pi pi, so what I define here is that an algorithm learns pi with a grid RT in this dynamical prediction setting if for every sequence of observations of inputs and outputs, the loss, I took here mean square error loss, but I can generalize to any other loss function. So this means the algorithm's prediction at time t minus 1. I'm using the notation here that ut to 1, for example, is u1, u2, up to ut. That's kind of the notation I use. I use throughout the course. Then the algorithm on inputs u's and y's from up to time t minus 1. It predicts a yt, and the loss, the sum of losses is at most the sum of losses of any other policy in the class plus rt. So this is very, very similar to regret in online learning. The only difference here being that I assume something about the sequence of generated observations. Any questions? Yeah, Jeff?
For the corollary, you have an extra factor of t, but based on your definition above, should that be an average over the sequence rather than just the like for every sequence?
Well, I took here, so regret is defined as sum, not as average.
Okay.
So it sums up, all the errors sums up, and that's how I get the t.
But then on your like definition above, where pi one epsilon approximates pi two, don't you have that over the entire sequence up to time t that error is already less than or equal to epsilon? Or is that just
No, so you see the definition, this definition of approximation says for every time you have that the predictions are epsilon close. The predictions at every iteration. So by pi of, this is similar to the notation I used for reinforcement learning. Pi of some sequence is the prediction of the algorithm of the policy pi over that sequence. So given a history u1 up to ut and y1 up to yt, each pi in the policy class predicts something.
So this is every single prediction?
Every single predictor, yes. This for every y, you see, for every y and for every u. That's what I wrote there.
Okay, but it's not like the sequence of predictions. It's just like the
There is no sum. There is no sum here. It's individually over every possible history, this holds. For example, this class, pi ABC, if I take kappa to be infinity, then I know that it has regret 0 compared to any other policy, right? It's always accurate. It produces every single prediction accurately because there is an ABC that will completely be determine the next observation given the past. And what we have seen, so we proved last Tuesday that this pi h kappa contains epsilon pi ABC kappa for h, which was the dimension, and kappa, let's say, being infinity. So we proved that. We proved that, and in fact for epsilon being 0. So we proved that even for epsilon being 0, we can get an exact approximation if we take this class of all linear predictors that take d into the past, observations and outputs. It can completely accurately determine the future y if it came from a linear dynamical system. And we did that by using the Cayley-Hamilton theorem. Everyone with me? Yep.
Should we not be concerned about this saying for kappa equal to infinity?
Why are you concerned? I don't think you should be concerned. Why are you concerned?
I'm not concerned, but I'm just trying to pinpoint why exactly I don't need to worry about it.
Well, I didn't give you any algorithmic results. It's only a representation result. So representation power, the union over all kappa of this linear predictors and the union over all kappa of the LDCs are not equal, but one contains the other. You can make it quantitatively For example, if you have A, let's say A is bounded, B is bounded, C is bounded, I can actually give you a bound on the M and N that will reproduce the exact same class. And you can derive it as a homework exercise. We derive the shape of these M and N, if you remember. So they were the characteristic polynomial. So you can derive bounds based on the characteristic polynomial. But I don't think it's very material to our discussion, but it can be done. It's a good exercise. Okay, so there is a finite. For every finite bound on ABC, you can derive a finite bound on the linear predictor that will approximate it. It happens to be exponential in the magnitude, but that's fine. Any other questions? Why am I giving you these definitions? So first of all, I want to be precise what I mean by dynamic learnability. So I now defined what I mean by that. I want to predict with regret compared to some hypothesis class. Usually my hypothesis class is generative. I know my data came from a generative set of dynamics. And therefore, if I learn or I compete with the class that generated the data, I know that I'm doing well. I'm able to achieve low error. Second of all, it's important to state this hypothesis class precisely because many times it's non-trivial to learn them. For example, the class of this ABC, the linear dynamical predictor, this class. It's a non-convex class, right? It has all these powers of A multiplying the other parameters B and C, and we discussed it's a non-convex parameterization that's naively hard to learn. We were able to convert it to a convex class that contains it. So we need to be rigorous when we talk about learning. What do we mean? I have an efficient algorithm for learning a certain dynamical system. What do I mean by that? I mean I have an efficient algorithm. It's able to learn a class of dynamics. And that class of dynamics is interesting because it contains another class, which is actually the one I want to learn. Please let me give you a minute to ask questions about it. I kind of went through it maybe quickly because we only have like 3 or 4 classes left. And I really want to get to the very interesting stuff. But I do want to make it clear what I'm proving to you and what the algorithm is and what the guarantee is and why it is interesting. Yeah?
Could you repeat why it's non-convex?
This class? So this is also called linear dynamical controllers. Predictors, sorry. Every linear dynamical predictor is parameterized by 3 variables that are what? A, B, and C, right? Now, how are A, B, and C used to create a prediction? You take the past inputs and you sum up over all of them, and you take B times A to the power times C. So you have a polynomial function whose degree is dependent on time. That's why it's not convex. It's not a linear polynomial. It's a high degree polynomial. There's no reason for it to be convex. On the other hand, the class of predictors that are linear predictors, this pi h kappa, that's convex. That's a convex class. It produces an output based on a linear function of the inputs. So before I move on, any questions about this formalization? This is important, okay? This is how I'm formalizing the whole problem of learning in dynamical systems. Question? Yeah?
Sorry, last Tuesday, the algorithm basically gives a zero regret
That's right.
approximation.
Yeah, that's right. What was the algorithm? Do you remember? Okay, I mean, once I have, look, this is what I proved last Tuesday, right? I proved this. How does this give rise to an efficient learning algorithm of linear dynamical system? I think that's your question. Does anyone here know? Can tell me? What is the algorithm I can use for learning linear dynamical systems? Yeah, Connor?
Kalman filtering?
We didn't study Kalman filtering. It's true, but we didn't study that. Alex?
Well, can you just do like Kalman gradient descent on that then?
Very good. So the algorithm, here's an algorithm. hidden dimension of the system I want to learn. So what does it mean? I can spell it out. Let's spell it out. I start with M1 to D and N1 to ND that are all 0. Let's start them all as 0. Then I see UT predict YT hat, the summation I MI UT minus I plus NI YT minus I. Then I see YT, and then I update so M and N at time t plus 1 divided by time t and 1 is going to be M and N time t minus eta gradient equivalent to M for N plus YT minus YT hat squared. And repeat. This is the algorithm. So what does this algorithm do? This algorithm online learns the parameters M and N from the class pi hk, where h I took the dimension d because I know that can represent the actual system that created the data. And using what we learned about OGD, the theorem of the first or second lecture, the regret of this algorithm is O of root t. This means that I can learn, in this sense, the algorithm produces a sequence of observations that compete with the best policy from the class ABC. So this is going to be 0, because the best policy from class ABC has 0 loss in the noiseless case, plus root t. Yeah.
Are there similar guarantees when we use like different loss functions? Like, for
Yeah.
example, like does it have to be mean squared error?
No, can be any loss function. So any loss function that we apply to OGD, any convex loss, remember this applied to any, there is nothing special about it. I mean, this is a generic algorithm, and this guarantee is also generic. So here you know what, I can even, let me write it. This is L, and here also L. So any loss function. There is nothing special about quadratic. Any convex loss function, Lipschitz convex. So this is a pretty strong result. Pretty strong result. I can learn up to 0 error, a sequence of observations. If they came from a linear dynamical system, I can use it to do this simple algorithm that does linear prediction from past to future will do it and get 0 error in the limit. When the system was indeed created by a linear dynamical system. If it was not created by a linear dynamical system, I compete with the best one. That's what the theorem says. Is it clear? This is very important conceptually, very important. Because I'm going to give you even a stronger theorem that I can learn any nonlinear dynamical system. But before I do that, I want to make sure that this is kind of understood. No objections? Good. So everyone agrees with me. This is a rigorous way to define learnability in dynamical systems. Yeah? And I already did something non-trivial because I was able to learn some non-convex, evolution of a system, and I'm able to learn it with an efficient algorithm. Okay. I'm going to give you another algorithm today for doing the same, solving the same problem of learning a linear dynamical system. Why is that so important? I want to get to nonlinear because the brain is nonlinear, but we need to go through this first. What is the issue, the main problem with the algorithm that I taught you? What's the main problem with it? Why is it not very practical? Yeah?
It depends on the hidden dimension.
Very good. It depends kind of mildly the number of parameters. So number of m and n depends on it. But still I have this dependence, right? It's very good. Now when you have a complicated system, who knows what the hidden dimension is? It could be very high. So important goal I want to be dimension independent. Or at least mildly, maybe logarithmic or something. Dimension dependent is, it could be huge. That's a big bottleneck computationally and also information theoretically in terms of regret guarantee. For this reason, I'm going to consider a subclass of linear dynamical systems that I can do what I want to do next. So I want to consider LDS, which are parameterized by A, B, and C, such that first A is going to be at most 1 spectral norm. So I'm going to allow up to 1 and not more than 1. This is not a big constraint because if it's bigger than 1, the output can explode even without noise, right? It will grow bigger and bigger. So that's not a big constraint. But 2, this is a bigger constraint. I'm going to assume that A is diagonalizable over the rings. So I'm going to assume that. And that is a big restriction because many systems can have complex transitions, asymmetric, or that have complex eigenvalues. The diagonalizable is not a problem, but the real eigenvalue, that's a restriction. Why do I assume that? Well, in full generality, getting rid of the dimension is actually possible. This can be proved. So I have to restrict myself somehow. And this is one restriction which seems reasonable. So I still allow marginal stability. I allow things to not shrink over time, even if there is no noise. Eigenvalue can be 1. And I still have the linear evolution. I can have very high dimension. But I'm restricting myself to this real eigenvalues, which you can say, is this restrictive or not? It's restrictive, but how much, that's debatable. Good. So now, I want to learn this class of LDS, okay? That's what I want to learn. So let pi star is going to be the set of all pi LBC linear dynamical predictors that satisfy 1 and 2. Okay. I want to learn pi star. If the data came from pi star, it means I will approach 0 error on average. And what I want to show you, we will see efficient algorithm for learning pi star without dependence, without the dependence on the. So this is very significant. Not depending on the hidden dimension is very significant. I can only take the inputs and observations into account and be able to learn in the sense that I described. Regret compared to the best predictor on class and all that. I want that to be small and without dimension. The way I'm going to do it is I want to define a policy class which I call PySpec for PySpectral. Let me define what it is. It is the set of all policies phi parameterized by m1 to mk. So let me call this PySpec k. And on input u t to 1, y t to 1, this is going to be summation I from 1 to k, and I in a product phi I phi, let's just take phi I transpose u t to 1. So I take some a linear combination of some inner products. Now I need to tell you what these phi i's are. Phi i's are vectors in R to the T. They are eigenvectors of HG, which is the Hilbert matrix, which I define like this. Hilbert matrix of order Now I need to say what is u ut to 1. I'm going to denote it ut minus 1 up to u1. And then I need this to be length big T. So then I'm going to fill it up with zeros so that this thing is an R to the big T. So just pad it to zeros. So then this is well defined. It's an inner product between a vector and R to the T and another vector R to the T. Question?
I was going to ask this.
Okay.
Is condition 1 the determinant, or is it supposed to be a spectral radius?
Spectral radius, but because I allow eigenvalue to be equal to 1, the spectral norm is okay too. And I also real diagonalizable, so yeah, it's the same here. The matrix is real diagonalizable. So basically it's symmetric, spectral radius and spectral norm are the same.
So like that's not a determinant, is it? Like we're not allowed like,
No.
we're not allowed like eigenvalues of 2.5.
Let's do whoa. Yeah. Questions? Is the policy class clear what it is? I didn't give you an algorithm yet. I didn't prove anything. But I'm just defining a policy class. This is a policy class. It's some family of predictors, which takes the history and predicts the future based on the history. How does it do it? It takes some vectors, which are eigenvectors of some matrix, and then multiplies by the inputs, and then projects with the m's. Yeah, Arnav?
Wait, sorry, is big T being fixed somewhere?
Fixed. Number of iterations fixed ahead of time.
Like pi k spec T, I guess.
Yeah, I guess so. Yeah. Yeah.
How does phi depend on I?
There are, okay, good. So there are, how many vectors, eigenvectors are there? There are T eigenvectors, and I take the first K, those that correspond to the largest eigenvectors.
Okay.
So, yeah, so that needs to be said. So phi 1 up to phi T are eigenvectors of HT was falling into eigenvalues, lambda 1, which is bigger than lambda 2, which is bigger than lambda tau, lambda 2. Yeah, Joshua?
What's the point of the Hilbert matrix? Like, why are we looking at this eigenvector?
The Hilbert matrix?
Yeah.
It's not clear yet. I will show you, but it's not clear. But I just need to define. I mean, is the class clear? That's all I'm asking right now. Class is okay? Yeah.
The inputs are all scalars?
Sorry?
The inputs you are all scalars?
No, they can be vectors. In which case,
It's gonna be, yeah.
this is multiplied coordinate-wise by the vector. Maybe I should start with. No, it's okay. It can be vectors. Vectors is fine. I don't want to redo. I can do scalars, but yeah, we can have vector input, vector output. Yeah, I mean, at this point, it should not be clear what is this matrix doing here and why am I looking at this matrix at all. But it's kind of a magical thing that will pop up, and then you will see how beautiful it is, that it works. But you really need this magical thing to allow you to get rid of the dimension. I don't know of any other way to do it. Actually, maybe now I do know, but also not trivial. There's another way to do it.
Are there any good facts about the Hilbert matrices?
Yeah.
That is the reason why we were even thinking about them?
Yeah. The main reason you will see in the analysis, that's the main reason. But an interesting fact about this matrix, which has been known for a long time, so fact, lambda I scales like e to the minus I over log t. It decreases exponentially. The eigenvalues decrease exponentially. So around log t, they become close to 0. Very fast. So even though it looks like it's a full rank matrix actually, if this matrix is full rank, it's t by t, you can check, it's not degenerate, and it's symmetric of course, it has all positive real eigenvalues. Nevertheless, its effective rank is something like logarithmic because of this phenomena here. So this was proved, for example, by Beckerman in 1000 in 2016. But actually it's known, it was kind of known empirically before. This matrix is goes back to Hilbert, 100 years or whatever. It's a very important matrix. Yeah, Kia?
I just have a question on notation.
Yeah.
We're defining the policy class up there for the vector. Is that the t power, or is that transpose?
This is transpose.
So that'll be.
Let me use this notation. I will do like left angle, right angle, like this. Is this okay? Yeah, like inner product. And indeed you need that because like I was asked here, so u can be a vector, in which case I mean multiplying all its coordinates by this same number. That's what I mean. Yeah? Is the class clear? It's an efficiently computable class, right? If I give you these m's, it's linear. This is a class of linear predictors. I can very easily optimize over it by Onel gradient descent. Is this clear? Elijah, what's not clear?
You multiply every coordinate by the same number.
Yeah.
Sorry, what does that mean?
For simplicity, let u1 up to ut and y1 up to yt be real numbers. Okay, for now. They don't have to be. Everything is going to be well defined even if I take vectors. They really don't have to be. But other than that.
That was the only thing.
Okay. Okay. Questions?
Wait, so the real numbers and the vector that you're multiplying by, is that just one?
No, why is it 1? The vector of u's, you're asking?
5.
is the eigenvector of this matrix. It's,
Oh, is UT21 a vector of all the U1s, UT?
yeah.
Okay, okay.
This is a vector of, you see, UT minus 1, ta, ta, ta.
Oh,
Okay.
oh, okay.
Yeah. Maybe the following needs to be, maybe, if it's clear to you, you got it. So I can run online gradient descent of this pi spec, and it's a convex, it's in fact a linear class of predictor. If you got that, you're good. Is this clear that this is what's happening here? Jeff, what's up? You have a question?
Oh, no, I was just looking at, so UT is, where's the T index there?
T to 1.
T2 one, okay. So,
Yeah, like this.
is that a capital T?
This is a small t. So a time little t. This is y hat t plus 1. So this is kind of what the policy says on input up to t. It gives you the prediction at time t plus 1. And that's how it's created. It's ignoring the past y's, use only the u's in a linear way.
And you only cut off, or you only take the first decay.
Yeah. Yeah, I only take the first k. And the reason for that is this exponential decay, which you will see. Yeah, Conan?
Would it be like better to say U sub T to T minus big T?
Yeah. It would be. I'm not going to do it, but it would be better to do it.
It's like just the buffer.
Yeah, that's right. I kind of fill it with zeros. Everything that's not there, I fill with zeros. Yeah. Okay, folks. Class is clear? Class of predictors? I should say this is a pretty advanced material, and yeah, this is difficult material. I don't expect you to come up with this kind of stuff on the exam or your homework. This is kind of difficult material, but state of the art. So let me now give you a theorem, which is the main theorem I want to prove. This pi h spec epsilon approximates phi star for h, which is O of log squared q over epsilon. So this means for every possible linear dynamical system that satisfies it's less than 1 and it's real diagonalizable, I can find a spectral predictor, like the one I've defined, that approximates it up to epsilon. And how many filters does it need to take? Very few. So this k parameter over there only goes up to something like log t. So it's very small. Yeah?
Sorry, what's H?
H is the order. Did they call it K? I'm sorry,
Yeah.
I call it K. Okay, so K. Yeah. Okay. Is it clear what I want to prove and why I want to prove it? And if I prove it, I'm kind of done. Because then I can learn the spec class instead of the original class. The original class is non-convex. I don't know how to learn it. It's hard. But I can learn this other class that's easier. It's convex. And by that, I learn any linear dynamical system. Yeah?
Have we shown any results for like how big T should be? Like.
That's just a matter of how many iterations you have in your prediction. Same as what we had in prediction from expert advice, or the first part of the course. You can think of like number of iterations. That's how many prediction iterations you have. It doesn't need to be bounded in advance, by the way. So if you don't know it in advance, you'll do doubling tricks and stuff like you had in your homework that you don't need to know T in advance. You can double it. It's just for kind of easiness that I'm kind of plugging in a fixed value.
So we can double it with this.
You can double it, not a problem. Yeah. That's a good homework exercise. Yeah? Any other questions? Good. So now, I need a small lemma to prove this theorem. And the lemma, this lemma is actually where the Hilbert matrix is going to show up, and that's kind of all the magic. And this lemma says the following. Let mu alpha be the vector which is 1 alpha alpha squared up to alpha to the t. Then for all alpha, the inner product between mu alpha and phi I is bounded by something like t squared e to the minus something like I over 4 log t. So this inner product between the ith eigenvector of the Hilbert matrix and this particular mu alpha vector is going to be small, going to be exponentially small.
Is alpha bounded?
Sorry?
Is alpha bounded?
Alpha, yes, alpha is between 0 and 1. I wonder if I should first prove the lemma or first prove the theorem. Maybe I'll first prove the theorem because that's very easy, but you kind of don't see where the magic is at this point. Nevertheless, I'll just, assuming this, let's see that we're good, and then I'll prove the lemma. The lemma is where the magic happens. So, theorem proof of theorem. So I want to show that using the spectral predictor, I can basically approximate any other policy in the pi star world. So let's consider any pi in pi star. Then I know that yt of this pi is equal to summation over I c a to the I minus 1 b u to the minus I. Right? That's what it's equal to. That's the prediction. And in fact, it's accurate if indeed the data came from a linear dynamical system of this property. It's actually exactly accurate. Now, by my assumption over A, it's diagonalizable over these numbers. So let me diagonalize it. So this is summation over I. And then I have C u d to the I minus 1 u transpose d u to minus I. So all I did is I diagonalized A into u d u. Now what is this D? This D matrix is basically a diagonal matrix where I have here, it's all zeros, and here I have alpha to the I minus 1, alpha j. So from alpha 1 here up to alpha d, and they're raised to the powers, right? To all the different powers. Yeah, Alex?
Wait, is this assuming that A is symmetric or diagonalizable?
Real diagonalizable. So diagonalizable over the real numbers. C U. Then here I have a summation j from 1 to d, alpha j to the I minus 1, U j Ej transpose. These are the standard basis vectors. U inverse B, U t minus I. And what I can do now is change the order of summation, move these vectors. This Ej I'm going to multiply by here, and this Ej transpose by this matrix here. And I can rewrite it as summation j from 1 to d, little cj, little bj transpose. So this little cj is the jth column of cu, and so inverse is fine. So bj is going to be the jth row of u inverse b. And what I have in the interior is summation over I from 1 to t, alpha to the I minus 1, alpha j to the I minus 1, ut minus I. So I just rearranged, kind of changed the order of summation. And this is now summation j from 1 to d. Let me just call it mj. Till. And here I have mu alpha j, ut to 1. Everyone agrees? Okay. Very good. So now, let me take yt pi yt star. I'm going to take it to be summation j from 1 to k, and j till u alpha j ut. Notice that this is a member, this belongs to pi spec k. Everyone agrees? So therefore, hence, if I look at yt, the real yt pi, minus yt star, what's the, let's take note. What's the difference? Well, everything cancels out. I'm only left with the terms from k plus 1 up to t. Of this mj tilde something something. And by Cauchy-Schwarz, this is less than some t terms, and each of them is this kind of mu alpha j transpose times ut to 1, which is less than t e to the minus j, basically the sum over j. So t times sum over j, e to the minus k over log t. This is all up to constants. And this is by dilemma. And here I have a sum over a geometric sequence that is bounded by the first item. It starts from k plus 1 up to t. So this whole thing is less than maybe 2t e to the minus k over log t. And you remember I took k to be log squared, right? So this is less than, much less than epsilon by choice of k.
So, all we did was, we said y star is just going to be the first k terms of this.
Yeah, that's right. In the different bases, right? I mean, I transferred it to a different basis, the spectral basis. The spectral comes from this is the very structure of the linear dynamical system. You see, it has the structure inside of it. It's hidden inside of it. It has these powers of the alphas. So that's why I transferred it to that basis, and I only took the first k terms, and I know that it decreases exponentially, so therefore I don't need too many of them.
So for the lemma, we use the eigenvectors of Hilbert matrix.
Absolutely, yeah.
But for here, it's ut to 1.
Sorry? UT to 1, yeah. Oh, lemma? You're right. Good. Wait a minute. So, I did mess up something here. Yeah. Yeah, sorry. I missed something here. So this is okay. Let me. You're right. I forgot a term here. Let me. So my bad. I missed the term here. So okay. Now here, I want to change the basis here. Okay. So I'm going to write it like this. So this is summation j from 1 to d, and j tilde, and then here I have mu alpha j. I want to put here identity, so summation k from 1 to t, phi k transpose ut to 1. And now I will take these. So this is just the identity because it's an orthogonal basis. So what I have here is summation j mj tilde. And now I have here the following. So summation k mu alpha j phi k ut to 1. This is bounded by t. I just have an eigenvector, which is a unit vector bounded multiplying the t components. And now I have these phis multiplying the mu j. So summation k from 1 to t, mu alpha j, times something which I'm going to call it t times some other m tilde j. Okay, and now I can take only up to h. H is the limit where I cut it off. So I can take y t spec to be same thing. Summation j, summation k from 1 to h. What's written here? T and j to 1. Now everything bigger than h, I will take the same thing. So I only took up to h. Everything bigger than h is going to cancel out and be destroyed. But still, that's not where the magic is. Okay, this is kind of a small typo, but there is nothing really substantial here in the algebra. So yt pi minus yt spec is going to be bounded by summation over a bunch of terms, but basically I have for j from 1 to d, and then I have summation k from h plus 1 up to t of something that looks like mu alpha j phi k times many terms, and this thing is going to be small. So this whole thing is going to be e to the minus j over log t times t times a bunch of other things. Yeah.
So the general idea of this theorem is that you can just get rid of this dependence on this hidden dimension because after a certain point, because of this lemma, like terms are just like edge.
Yeah, yeah.
Like effective rank of.
Yeah, the effective rank across time is low. So I need, the amount of filters I need is like log t, log square t, and after log square t terms, things start to decrease very, very rapidly. So that's kind of the main point.
And there's no, I guess, extension of this to like, I don't know, if you consider just like a more generalizable class of A's, being like, you just like if you do this with Jordan matrices, it doesn't work out well.
Jordan might work, but complex numbers no, just not true anymore. So full generality, it ceases to be true. But there are other things you can do. So I will show you, hopefully next lecture, how to extend it further. Okay, so my apologies on the algebra here, but I did miss the identity here. So again, I'm putting in the identity in the middle. That's the sum of all orthogonal eigenvectors. This can be done with any vectors, nothing special. And then I only need to sum up to the eigenvalues that are small because of this lemma here. So this lemma is the main magic. Yeah.
Sorry, but how's this dimension 3?
Well, where do you see the dimension?
Are we still like summing over from 1 to 2, right?
Yeah, but you have norms. It's not, there is no, you have a sum of norms of numbers. It doesn't have any, and I can sum it up. I can sum up all of them. So, kind of got lost in the algebra here, but I can basically sum up these across the dimension and get a bound. It will not come outside. I'm not doing Cauchy-Schwarz across the dimension.
Okay.
That I'm not going to do. So, I think I won't have time to go back into this. Maybe let me wrap up the lemma and then I'll see if I can go back into this. But it doesn't pop up. Only the magnitude of it. Yeah.
Over there in YFT spec,
Yeah.
what's H on the second dimension?
This is the H of the spec spec class.
Which is K.
Which is K. Yeah, I use K unfortunately for two different things. So let me move this back into H. So that's kind of history. How many I take? How many vectors do I take? All right. So last thing I want to see is the lemma. Okay. So now let's prove the lemma. So I want to prove that for any alpha, mu alpha times phi I is less than something like e to t e to the minus I over log t. That's what I want to prove. So let's look at the function g of alpha. I'm going to define what is mu alpha transpose phi I squared. That's what I'm defining. Inner product squared. Function of alpha. alpha at the area, so alpha is from 0 to 1, and it's some non-negative function. Let me start by bounding the area under the function. So integral alpha from 0 to 1, g alpha d alpha. This is integral alpha from 0 to 1. And what I have here is phi I transpose mu alpha transpose phi I d alpha. Right? So this is phi I transpose integral over alpha mu alpha transpose d alpha phi I, which is phi I. Now notice what do I have here? I integrate from 0 to 1 the vectors that are 1, alpha, alpha squared, and so on. So this is going to be something like 1, alpha, alpha squared, and so on. D alpha. And if you integrate it from 0 to 1, you will get exactly the Hilbert matrix. Which is why I chose these phi's to begin with. Okay? So this is lambda I, and by Betterman-Townsend, this is less than e to the minus I over log t. Okay, that's why I chose it like that. So this is where it comes in. Now, this is a uniform bound over all alphas from 0 to 1. It's not an absolute bound. I claim that this is true for any alpha. However, you can say the following. When you have a function that's non-negative from 0 to 1, it's non-negative, and it has an area bounded by something. Let's call this big A. This is AR, area. How tall can it be? What's the maximum value it can obtain? It's Lipschitz. The G prime, if you look at the G prime here, that's 2 times with respect to alpha, and mu alpha phi I. So this thing is bounded by t or something. It's not, the derivative here is not bigger than t. So it's a Lipschitz function, and it's bounded it has some area in 0 to 1, it's bounded by t. What's the largest area it can have, or what's the largest maximum it can have for a given area? Well, it reaches a maximum here. The most steepest decline it can have is t, like this. That's the worst that can happen. So area, or I should say the G max, is less than the area. So divided times t, times the Lipschitz constant. Okay, so t times the maximum is the upper bound on the area. Cannot be more than that. So this is less than t e to the minus I over log t. Okay. So I'm using the fact that this area, I know what it is, it's bounded by what's written here. The maximum cannot be too big. So the area is lower bounded by that of this triangle, which is max times 1 over 2. That's the area. Okay? It is a factor 2. Good. So I'm almost over time, but that proves the lemma. The lemma is what gives rise to the theorem, approximation theorem, and the approximation theorem is what allows me to later get an efficient algorithm for all linear dynamical systems that have these properties of real diagonalizability and eigenvalue bounded by 1. Questions? Yeah.
So this t is the Lipschitz constant, not our big T.
Not our, not what?
The big T that we're talking about, like the different derivations.
Well, it's the same because this, you see that, so this phi is an eigenvector. It has the norm 1. And then this is alpha squared, it's not more than t. Okay, so the dimension of this vector is r to the t, multiplied by Cauchy Schwarz, basically. I'm doing Cauchy Schwarz. Okay, so it's the same. But even if I had dimension here, that doesn't matter. It only goes into the log, you see. So what I have here, because of the exponential decrease, the important parameter is the what's in the log. Everything outside will be eaten up to logarithmic factors. There's a question over there? Yeah?
Yeah, I guess if those initial conditions are, like if I have some linear dynamical system where those initial conditions aren't met, are there such ways to like represent it in that way, or?
Yeah. So that's what we're going to do Thursday, actually. I can convert any linear dynamical system to this form. And that's what we're going to do Thursday, and then hopefully next week, any nonlinear dynamical system, I will convert it to this form. And that's how we can learn any nonlinear dynamical system by convex optimization, so provable guarantees. Yeah.
Sorry, when you say convert it to this form, what exactly is this form?
This is on Thursday. But okay. You're asking what? So that pi star, which I defined, I don't know where it is now. Oh, it's maybe here. So pi star is the form of LDS that I'm considering here. It's an LDS that has spectrum radius bounded by 1. It's diagonalizable over the reals.
You can convert any linear dynamical system into one where...
Yeah. Convert in some very special sense that it makes sense for next token prediction. I cannot convert to get the same control, but I can convert in terms of observation, which is what I need for prediction. Prediction, I only care about the observations that I see. That's all I care about. I don't care about what's going on under the hood, not very important. More questions? Yeah?
In the lemma there, you said t squared. Is that a typo or no?
Phi squared? Where do you see phi?
T squared?
Well, it's also true with t squared. I take some slack because I never know what the constants will end up to be. Yeah. Okay, good. See you Thursday.